Okay, so I think we can start. So today in the seminar series we have Federica. So she did the PhD at IFIC in Valencia, and now she's a postdoc in France, in Nantes, Subatech. And she's been mostly working on neutrino properties, neutrino physics, and beyond standard model with Corco Lab Supernova neutrinos. And today she will tell us about the results of her last two publications.
Thank you very much, Marta, for this introduction. Yes, I want to also specify that at the moment, even I recently started a more experimental postdoc here at Subatech with Indexino collaboration. But despite this, I'm still active and extremely interested to neutrino phenomenology, and very happy to engage any kind of conversation. So please feel free to interrupt me at any moment during this presentation. And yes, today I'm going to present you some results that I obtained during my PhD about the possibility of, for a future detection of Corco Lab's supernova neutrinos to shed light on neutrino properties. Okay. Neutrino within the standard model are described like weakly interacting particles, which appears in three flavors, depending on the outgoing electron that is produced following their interaction. They are electrically neutral and also, of course, massless. However, nowadays we know that the description that the standard model provides about neutrinos is not the correct one, because we know that neutrino oscillates. The quantum mechanical phenomenon neutrino oscillation is related to the fact that the neutrino weak eigenstates do not coincide with the neutrino mass eigenstate, but can be described as a combination of the neutrino mass eigenstate weighted by the elements of the leptonic mixing matrix, which is called also known as PMNS mixing matrix. So the phenomenon of neutrino oscillations, neutrino flavor oscillation, allows to neutrinos to change their flavor from the production point to the detection point, due to the fact that the different mass eigenstate oscillates with different frequencies. The oscillation probability can be expressed by this analytical expression, and it depends on the element of the mixing, the leptonic mixing matrix, as well as on the neutrino energy and the baseline that the neutrino traveled from the production to the detection, and also from these delta m square parameters, which represent the differences among the masses of the neutrino mass eigenstates. This phenomenon have been observed and confirmed the fact that the neutrino must have non-zero masses, even if very small masses, and the importance of the phenomenon for neutrino physics has been also demonstrated by the Nobel Prize in 2015. Massive neutrinos also open the possibility for them to decay during the production, during their path from the source to the detection point. The discovery of neutrino masses, of course, generated a lot of still open questions in neutrino physics. First of all, the most urgent one related to the absolute value of neutrino masses, since we do not know what these values are, and also related to the neutrino lifetime, if neutrino are stable or they can actually decay. but also more other question related to the actual neutrino nature, if Majorana or Dirac nature, and this is something that is being studied current investigation by neutrinoless double beta decay experiments. And then we have also the mass ordering problem, which basically express the fact that we don't know if the third neutrino mass eigenstate is lighter or heavier than the other two. In this talk, I'm going to focus on these two particular specific open questions related to the neutrino mass and neutrino lifetime. In particular, I'm trying to address these two questions. What is the value of neutrino mass, and do neutrino decays? But actually, more than give a concrete answer to this question, I'm going to explore the future neutrino landscape in terms of future possibility that next generation neutrino observatory can give on these topics. Before presenting the results, I'm summarizing in these slides the current state of the art regarding the neutrino mass measurement on the left and the decay, the neutrino decay measurement on the right. You see that nowadays we have a lot of constraint that has been put on different by different experimental collaboration, exploiting experimental technique and looking at different neutrino sources. For example, regarding neutrino masses, bounds from cosmology, we have bounds from direct kinematic measurement, like the recent one of Catherine. We have also constraints coming from neutrinoless double beta decay measurement, in particular through the effective Majorana mass parameter, which is directly related to the absolute mass scale and also to the mass ordering. Finally, also with the supernovae observation, the only one that we have had so far, exploited time of flight measurement. Regarding neutrino decays, again, we have several bounds on this tau over m parameter, which is the one that can be constrained experiments so far, exploiting different neutrino sources like atmospheric, cosmogenic, high energy from high energy neutrinos, and again from supernovae. The goal of this of the work that I carried out has been to find how the future supernova neutrino observatory could improve current bound on neutrino mass and neutrino decays already defined by Supernova 1987A. Before starting, a small explanation of what is a core collapse supernova. A core collapse supernova explosion represents the final stage of massive star's life, when all the nuclear fuel has been already burned and an iron core is formed. Here, the neutronization of the nucleus allows for some neutrino fluxes to be propagated and injected from the stellar environment until the nuclear density is reached within the core and neutrinos stay trapped within the stellar environment. A protoneutron star starts to form, and all the infalling materials start to rebound and trigger shock waves. These shock waves are fed by the neutrino radiation, which is still locked in within the stellar environment, until the density conditions allows the neutrinos and all the shock waves to move outside, ejecting all the surrounding material as well as neutrinos, and leading to the cooling of the protoneutron star. This process leads to a large emission of neutrinos of all flavors with energies of on average on tens on MeVs within a 10 seconds time window. Why supernovae are important to study neutrino properties, to perform neutrino physics? Well, first of all, because we already observed a neutrino signal coming from a supernova, and again the supernova 1987A, from which we have been already capable to put some bound on several neutrino properties, as the one that I showed you in the previous slides on neutrino mass and neutrino decay. Secondly, because supernovae are neutrino factories, since almost all the energy released by their explosion is emitted by neutrinos of all flavors with mean energies of tens of MeV. And finally, because they represent cosmic laboratories in which particle physics can be studied under very extreme conditions that cannot be reproduced by human-made or nor Earth-based laboratories and experiments. The negative aspect of doing physics, neutrino physics, or whatever with supernovae is that we do not have control on when nor where the next one will occur. This sketch represents the expected core collapse supernova distribution within our universe as a function of the distance to the Earth. You can see that basically the density, the expected rate of core collapse supernova increased by increasing the distance to the Earth. But the expected rate that we can observe from supernova neutrino interaction within our experimental devices decreases as the distance square. So with the current and the future experimental setup, what we can aim is just to observe supernova burst in near galaxies, meaning at the distance scale of the kiloparsec. And another interesting aspect is that according with some estimates of the star birth rate within our galaxy, we could expect among 1 to 3 core collapse supernovae per century. This means that we could be very close to detect the next one. So in order to be successful with this goal, we should be prepared. The neutrino emission from a supernova can be divided into 3 main phases. The initial one is the so-called neutronization phase, which lasts for about 25 to 50 milliseconds from the iron core collapse. And it's characterized by this sharp peak in the time energy spectra of the electron neutrino component of the supernova neutrino flux. Then we have the accretion phase, which lasts for about 1 second, and then the final cooling phase, which can extend up to tenths of second after the core collapse. In this plot, I'm comparing the behaviors of neutrinos coming from 2 different supernova progenitor taken by the Garching modeling simulation group. Of 2 different masses, one of about 9 solar masses, which is depicted in solid line, and the other one of 19 solar masses, which is the one shown in dashed. An important thing that I want to underline looking at this plot is the fact that in this very initial stage of the supernova neutrino emission, the so-called neutronization phase, you can see that the luminosity, the mean energy, the feature of supernova neutrino emitted do not vary significantly among the two selected progenitors, something that actually happened for the other two phases. This means that the neutronization phase actually represent a robust and, let's say, model-independent prediction of the supernova theory. So the first result I'm going to comment is the sensitivity from future observatory to the absolute value of neutrino mass. Neutrino masses are introduced can be introduced through a time delay. This time, a time delay that is parameterized in this way, and which basically express the delay with which a massive particle propagates respect to massless one. The effect of this time delay is the one to produce a deformation of the expected rate, the expected neutrino flux in the time and energy parameter space, and it is inversely proportional to the neutrino energy, meaning that lower energy neutrinos acquire higher delay, so arrive at the detector later than more energetic one. In order to perform our analysis, we selected two among the future supernova neutrino observatory, which are the Hyperkamiokande 1, which will be located in Japan, and the Deep Underground Neutrino Experiment DUNE, which will be located in United States. And we selected these two because they exploit basically two different interaction channels, which allow for a multi-flavor observation of the next supernova neutrino emission. Hyperkamiokande will be a water Cherenkov detector, so mainly sensitive to inverse beta decay interaction of electron antineutrinos on free protons, but also sensitive to elastic scattering on electrons of all flavor neutrinos. And with the gadolinium hypothesis, these two interaction channels can be actually separated, and this can be disentangled and treated at statistical independent channels. While the Deep Underground Neutrino Experiment, in particular its far detector, will be constituted by 4 modules of liquid argon time projection jammer, so mainly focused on the electronic component of the supernova neutrino flux through charge current interaction with argon nuclei. Assuming a supernova distance happening at 10 kiloparsec, we perform our analysis in order to study the mass bound that can be achieved with DUNE. Let me explain a bit the structure of this slide. So this plot on the bottom left represent the expected rate, the expected neutrino rate as a function of time, with a zoom in the neutronization peak time window. And I represented in red the normal ordering, while green represents the inverted ordering case. In these tables, I'm reporting the expected rate for both time windows, so the whole 10-second supernova explosion, the whole 10-second time window for the supernova explosion, and just the focus within the neutronization peak for the two discussed, for the two selected supernova progenitors. And I'm reporting here also the number of known oscillation just for comparison. And the last column represents the bounds that I got in the two different cases for both normal ordering and inverted ordering. Some consideration about these results. First of all, you can see from in both cases that the best result that is achieved is the one of inverted ordering, so the green one. The most stringent result is the one of the inverted ordering case, even if the overall statistic collected during the explosion is lower than the expected one in normal ordering case. And this is due to the fact that in inverted ordering, we still have the information that comes from the neutronization peak, while in normal ordering, this is suppressed for MSW effect happening, for the matter effect happening within the stellar environment. So the presence of this peak allows us to set a stronger constraint on the even if the expected statistics is lower. And another interesting fact by comparing these two results is that the two cases, the result obtained in inverted ordering are consistent among them, are very close to each other, while the one collected in normal ordering strongly depend on the progenitor mass that on the progenitor mass that I'm assuming. And this is due to the fact that always related to the absence of this neutronization peak information in the normal ordering case. To set this bound, the analysis relies on the all statistics collected during the explosion, which in this case, the larger statistics is expected for the higher supernova progenitor. We repeated the same analysis, now assuming the hypercamiocande detector. So now we have two different interaction channels. The main inverse beta decay one, which is the dominant one, and you can see that it is dominant from both the plot as well as the number reported in the table. But also we have the presence of the electron, the elastic scattering of all flavored neutrinos with electron, which you can see can give us some hints of the presence of the neutronization peaks due to the fact that these channels is sensitive to the electronic component of the supernova neutrino flux. The results that we got in this case, of course, due to the fact that the expected statistics is more or less the same, let's say, in both in all the oscillation ordering. This is the reason why we do not have a strong separation among these two orderings. But you can see that basically the expected the statistics coming from the elastic scattering channel, which is the one that leads the imprint of the neutronization peak, is of course negligible compared to the inverted ordering case, to the inverse beta decay case. But the presence of this statistic allows us to get improved bound compared to the just considering inverse beta decay interactions, because again we have access to the peak, to the electronic peak component. From this analysis, the result that we got is that the future neutrino observatory Dune and Hyper-K can improve the sensitivity that we already have from supernova 1987A, which is currently set to 5.8 at 95% confidence level, 5.8 electron volt. The last results that I'm going to discuss is related to the possibility for massive neutrinos to decay. And in this particular analysis, we explored the scenario in which a neutrino decays into sterile states. So we have no access, we have no knowledge of the decay products. We cannot measure them within the detector. And again, we should include the effect of massive neutrinos in the same way as done before by including this time delay. But now we should convolute the effect of neutrino masses via time delay to the effect of the flux suppression due to the neutrino decay along the path. This is the deflection factor that we applied to our analysis, which is dependent on both, of course, the distance that the neutrino travel, the neutrino energy, the neutrino mass, and also the neutrino lifetime. In this case, since we are actually not interested so much in detecting the neutronization looking at the neutronization peak directly. In this case, we just want to see the effect of a flux suppression. And to make this, we selected among the two previous chosen detector the ones that can collect more statistics. So we focused on the Hyperkamiokande, again considering the two different inverse beta decay elastic scattering channel under the gadolinium hypothesis, and then combining the result that we obtain in both cases. And these are the results that we obtain. In particular, this is the result that we obtained by on this tau over m parameter, which is the one that has been constrained by experiments so far, and the one for which upper limit are reported, lower limit are reported, sorry, in the slide that I showed you at the beginning. But also we explore also the possibility for future supernova observation to put bounds independently on both the neutrino mass and the individual neutrino lifetime. And if we now compare the result that we have with the result that we got with the result reported in bibliography, we see that at least for this tau over m parameter, the future observation of supernova neutrino could improve the current bound set by supernova 1987A. Okay, this brings to my conclusion actually, and my conclusion on the potential of a future detection of neutrino signal coming from supernova and the impact that this could have in the neutrino landscape. First of all, I want to remark again the importance to detect the neutronization peak, especially within the neutrino mass, especially when trying to constrain the neutrino mass. This tool, this neutronization tool detection, constitute a complementary and let's say again model independent measurement to laboratory and cosmology feature results. And again, exploring the neutrino invisible decays with large statistics collected by HyperK or also future supernova neutrino detector could, of course, improve current bound and maybe open the possibility to extract simultaneously bounds on both neutrino mass and lifetimes. Future outlook. Of course, at the current stage of the art, we need advanced in supernova simulations, something that can be for sure provided by the next supernova explosion. So looking forward and waiting for the next supernova, core collapse supernova 1 to happen, because it could be a precious opportunity to shed light on both the dynamic of the stellar collapse, on the stellar collapse, as well as on the role that neutrino play in the explosion process. That's all. Thank you very much for the attention and again for the opportunity.
Thank you, Federica.
Thank
Any
you.
comments or questions?
Maybe I'll jump in with one. So on an early slide, you showed some of the cosmology limits on neutrino mass. So I'll just mention this is in particular the DESI measurement. So since I'm a member of DESI, I'll clarify because this has caused confusion. So that constraint on the sum of the neutrino masses, just FYI, is based on assuming lambda CDM cosmology. But you may also know that lambda CDM is actually not the favored cosmology in the DESI data. So if you relax that assumption and allow the dark energy equation of state to float, then this neutrino mass limit goes up by more than a factor of 2, and it becomes much more comparable to the Planck limit. So I just mentioned that because it's I know it's caused some confusion in the community where people are saying this is now like not agreeing with other measurements and is getting to the point where it's in conflict with oscillations. And so just to be clear it assumes the cosmology is actually not the best fit. Right.
No,
weird.
Actually, thank you very much for your comment because yes, I forgot to specify that I'm not a cosmologist, I'm not an expert of this, and I know all the debate around this DESI measurement. I'm not. I'm trying to stay tuned on the evolution of this story, but it's quite complicated if you are not of the topic. But thank you very much for specifying this. Thank you, thank you, thank you.
Any other comments or questions?
Yeah, actually, one question regarding your hyperchemical numbers. I mean, I noticed that you were looking at hyperchemical with gadolinium. So what kind of, I mean, was the 90% kind of, or actually, what kind of neutron tagging rate were you thinking about?
Yes. I mean, we are, sorry. We are assuming a neutron tagging efficiency of 90%. So we are assuming 90% of the total expected rate and 90% being inverse beta decay. And the 10% not tagged as inverse beta, so included in the other detection channel. So yes, probably a 90% of doping of gadolinium. Yes, probably I didn't mention this. Sorry.
Well, I mean, I think, obviously this is something which gets discussed as to,
no. I mean, of
whether
course,
whether gadolinium will go into the detector and all that kind of stuff.
Sure.
But it also occurs to me that the which I'm not sure is really taken into account enough. The electron scattering events are highly directional, but IBD is not. So if you can identify the direction, then you might very well be able to change these ratios quite a bit favorably.
Exactly. And you're totally right, because this actually has been, let's say, yes, as you already pointed out, a simplistic assumption. But of course, yes, elastic scattering is directional, and this could help us to add another discrimination, let's say, condition within this framework. But yes, totally agree, totally right. Thank you for pointing this. Thank you.
Yeah, I actually wanted also to comment on that because we don't. I think that the plan is not to dope hypercamiocandidates like we did with like it was done with the Super K.
Exactly, and this, in fact, this idea was more like. Okay, let's try to see what has been done with Super K, but without neglecting actually the current state of the art of the Hyper K. Of course, these are, I mean, very preliminary, very simplistic, very everything. But yes, you're totally right. These are just assumptions, and of course, if you change one, you change everything, and if you include one, you change everything again. So thank you again for pointing this. Thank you.
I see another hand by Jim.
Talking of assumptions, so I'm interested in exactly the scenario you're considering with neutrino decay. So here you have a neutrino decay into something.
Basically, we have just a neutrino decays into sterile states. This is again another very simplistic case in which we are not assuming any underlying model, just looking at the depletion of the expected rate.
Okay,
No.
so but if you consider an example, for example, where it decays, where one mass state decays to a different mass state,
sure,
for
sure,
example,
sure,
mass
sure,
3
sure,
decays to mass 1,
sure.
then actually, in the case of normal ordering, your neutronization peak now becomes much more visible.
Sure.
Because if it had stayed as mass 3, you wouldn't see it, but if it becomes mass state 2 or 1, now you do, and so that would completely change your limits, right?
Exactly, and this is exactly the next step of this. Thank you very much. Yes, sure.
Any other comments or questions, Ricardo?
Hi, can you hear me?
Hey.
Hi, Federica, how are you?
Hi.
I always have a similar question. I think we already spoke a little bit, but I forgot. So if we manage to do some kind of light curve, total light curve reconstruction of all the neutrino flavors, not with xenon and ton, but maybe let's say next generation in conjunction with dark side, something like that, would this be of particular importance, possibly actually to the first part of the slides? And how, or on you studying this, you think, for instance, it will be just completely statistically limited, or the actual just physics of it does not really improve a lot by having the complete light curve reconstruction?
That's a very, very nice question. And before replying to this, I want to think about this carefully, because I think that we already discussed something similar, if I'm not wrong. But let me think about, and I can get back to you.
Yeah, we were not sure at the time, so maybe also someone in the call had some inputs. I don't know. We'll discuss it in the future for sure.
So maybe I can comment on that, because you were talking for an all flavor measurement on dark matter experiments, which we know are statistically limited, as you were mentioning, because they are quite small, at least the generations starting now. But actually with with liquid scintillator, we will be able to have all flavors, not via SNEWS, but proton scattering. And since this time is 20 kilotons compared to the size of dark matter experiments, you would expect for like normal distance of 10 kiloparsec, like 1,000 events of neutral current of all flavors.
Right.
I see.
And does that impact directly any one of these measurements?
Yes, I guess, yes. Because, because at the end, is it true that there is the neutronization peak? It is completely true, but most of the time, statistics is the one that dominates. So, of course.
Okay.
Sure.
Okay, good. I mean, in the coming years, we'll study for XLZD, this next generation, maybe we'll come up with something. Cool. Thank you.
Thank you.
Sorry, in connection with that, do you also expect, someone would have to remind me, how many, say, sevens events you expect to see it do?
How many what? Sorry?
The coherent
coherent
elastic,
I no idea, because I
mean, as far as I know, for Dune, this has not been studied, because the current trigger they are considering does not allow for an low enough energy threshold for triggering SNEWS. I mean, it's in their pipeline for the low energy strategy for phase 2, when they will get more, but I don't think there's any study that already exists on that for.
Yeah, because I mean, clearly it's nice to be able to see both of these kinds of channels, both a charge current and a neutral current in the same experiment, resolves a lot of ambiguities.
Yeah, definitely.
Michela?
Hi, very, very nice talk. So I wanted to ask, so looking at these uncertainties here, maybe also referring to the essentially where you show how you actually evaluated the mass of the neutrino, the equation. What is essentially what is it driving? What is the main contribution to these uncertainties here?
Okay, this is purely statistic, but
okay.
I mean, in this case, are just statistics.
Okay, so can you show us back the equation where you show the how you evaluate neutrino
Which one,
mass?
sorry?
Where you evaluated the neutrino mass, the limit on neutrino mass.
I mean, this one?
Okay,
Okay.
yeah, it's okay. So I was just wondering, essentially, which systematics do you expect? For instance, how well can we actually reconstruct the timing of the neutrinos? And
Yes. I mean, in this case, in this particular case, the systematic way that we expect to be dominant are, of course, the one coming from supernova uncertainties. Because yes, even though I told you that the neutronization peak is, let me go back. Okay, I can use this. Of course, that if we look only at the neutronization peak, maybe some uncertainties on, I don't know, cross section or time resolution, energy resolution, whatever, could dominate. Eventually, I don't know the answer in this particular case. But if you extend your time window to the whole supernova 10-second time window, here the dominant systematics come from uncertainty in the fluxes. As you can see, the behavior of neutrinos, the normalization, the fluxes, whatever, is strongly dependent on the model that you assume. And here I'm just depicting two of the many possibilities that we have from different simulation groups, assuming different details of the supernova dynamics, microphysics, and whatever, equation of states. So the most systematic will come for sure from supernova uncertainties parameters, luminosity, mean energies, and pinching parameter.
Any other comments or questions? Okay, I don't see any, so we can thank Federica again.
Thank you very much again for this nice opportunity.